The purpose of this video is to tell you about the principles of titration so that you can do the lab exercise independently, being equipped with all the knowledge that you need about titrations in order to understand the experiment and to do the necessary calculations. So what is a titration? In a most general way, we can say a titration is a situation where we take a solution of an accurately known concentration, and let's say we put it in this burette. Take a look at this setup down here. And we gradually add that to another solution of unknown concentration until the chemical reaction between the two solutions is complete. When we say that, we mean that we have reached the equivalence point. So let me give you a simple example. Let's say we're reacting NaOH with HCl, strong base with a strong acid, and we generate a salt, NaCl, and water. So if we were to react 1 mole of NaOH with 1 mole of HCl, we would reach the equivalence point. Why? Because all the available base will have reacted with all of the available acid, and there will be none of either of these left. By definition, that's the equivalence point. All we have at this point is our salt and water. So here it says the point at which all the acid has completely reacted or is neutralized by the base. We call these neutralization reactions. But we could also flip that on its head. We could say the point at which all the base has completely reacted with the acid. Kind of depends on our setup here and what our knowns and our unknowns are. The final thing that you need to be aware of is something called an indicator and its purpose. It changes color just, I would say, just past the equivalence point. And I'll explain why. But let's imagine for a minute here that we are slowly adding a base to an unknown acid until something happens to that indicator that it changes color. So in here we have a base of known concentration, and in our Erlenmeyer flask, this is a burette, by the way, where the base is, we fill this burette with base. And down here we have an acid of unknown concentration. So known and unknown. Okay, we slowly add the base to this unknown acid until the indicator just changes color. Now, why would that happen? Imagine in this case, if this were our NaOH and this were our HCl, well, once we have reacted equal amounts of the acid and the base, neither of them has left. Is left. There's nothing left of acid or base. So at that point, if we dispense any more base into our beaker, it has no more acid to react with. And this solution here is going to become ever so slightly basic. Guess what that extra drop of NaOH is going to do? It's going to react with the indicator inside this Erlenmeyer flask, and it is going to change color. That's how we know we reach the equivalence point or the end point. We can use acid-base titrations for all kinds of chemical compounds. Here's another example where our HCl has basically been replaced by H2SO4. We're still using NaOH here. And then this is going to form, once again, water and our salt, sodium sulfate. One important thing to note here, though, is we have a different stoichiometric ratio. So for every 1 mole of sulfuric acid that we react, we actually need 2 mole of NaOH to reach the equivalent point. And that's going to become important when we want to quantify the amount of, let's say, sulfuric acid present in solution. So this time, sulfuric acid is our unknown concentration. And NaOH that we're dispensing through the burette into the sulfuric acid is actually of a known molarity. Now you might be wondering, how can we quantify exactly the molarity of sulfuric acid in this solution by doing this? Well, trust me, by the end of this video, you're going to know. It should hopefully make a certain amount of sense to you because we have like numbers we can play around with here. But I'm definitely going to show you specifically how this works. In a titration experiment, a student finds that 23.48 ml of an NaOH solution are needed to neutralize 0.5468 grams of KHP. What is the concentration in molarity of the NaOH solution? Well, we can infer a few things here. One is our NaOH solution is our unknown concentration, and we know exactly how much KHP we needed to neutralize this volume of NaOH. Now, KHP is probably a compound that you've never heard of, but it's a fairly common acid that is used to quantify a base of an unknown concentration because it's very easy to get a highly accurate concentration by making a solution of KHP. So we know a few things here. We know the gram amount of our acid. We know the volume of our NaOH. We also know that this gram amount, this 0.5468 grams of KHP is what was required to reach the end point. Let's ask ourselves a few questions now about how we can use this to get at the molarity of the NaOH solution, because this is our question. We want to determine the molarity of NaOH. And we know by definition that that's moles of NaOH over liters of solution. We're given milliliters actually in the problem. And as noted before, we're given the mass of KHP. We also have a balanced equation. So volume of NaOH given in the problem. Goal, find mole of NaOH. And then solve for molarity using this equation. We know we have a balanced equation for KHP and NaOH. It's right here. And we see from that this, again, 1-to-1 mole ratio of the reaction of the acid with the base. So now we can ask ourselves, how many moles of KHP are contained in 0.5468 grams of KHP? Well, once we have mole of KHP, guess what? We also know mole of NaOH at the endpoint. Once again, we're given the liters. So guess what? We can find molarity. Let's look at the calculation. So 0.5468 grams of KHP. Crucial piece of information that we need is the molar mass of KHP, and that will give us how many moles of KHP were required to neutralize the NaOH in our experiment. So basically we can say, given this ratio, we must have consumed 2.678 times 10 to the third moles of NaOH. Again, 1-to-1 ratio. We know moles of KHP, we know moles of NaOH. And now, since we know both moles and volume of NaOH, how do we know volume of NaOH? Because if you go back and look at the original problem, you will see that it was 23.48 milliliters of NaOH solution of unknown concentration. So now we take our moles of NaOH, we convert milliliters of solution to liters of solution because molarity by definition is moles over liters. And then we get 0.114 moles of NaOH per 1 liter of solution, which is just another way of saying 0.114 molarity. So what have we done here? We've taken a very accurate quantity of KHP that was required to neutralize NaOH of unknown concentration. We converted grams of KHP to moles of KHP. We used the balanced reaction, determined how many moles of NaOH were consumed. Then we used the volume originally given in the problem to get at the molarity. And now we have done something called standardizing our unknown solution, which is the molarity of our unknown base, which is a really important thing because it can be actually hard in lab to get a very accurate molarity by just measuring sometimes. One more problem to tackle. We just basically standardized NaOH. So now let's say we want to take that standardized NaOH and we want to use it to determine the concentration of an acid of unknown concentration. So now let's play like this is standardized. We are very confident about this molarity of 0.95 molar. So in our titration setup, it takes 25.5 ml of our standardized NaOH solution to neutralize 20 ml of H2SO4. And we want to know what is the molarity of the H2SO4 solution. Now notice this time we're not given any gram amounts, and we don't actually need them. What we do need, always, is a balanced equation. And we looked at this balanced equation earlier, but let's rewrite it. Is going to yield Na2SO4. SO4, sulfate ion, has a charge of -2, plus H2O. Now we have to worry about balancing this, so we need 2 NaOH over here to balance the Na. Now we have to put a 2 in front of our H2O. Let's see here, hydrogens are balanced, oxygens are balanced. We look like we're good to go here. Now, as I pointed out before, notice we have a 2-to-1 molar ratio of NaOH to mole ratio, I should say, 2 moles of NaOH required for every 1 mole of H2SO4. Okay, now one thing that we're given is that we have 0.950 mole per liter of NaOH, and we know to reach the equivalence point, we dispensed 25.5 ml. I'm just going to make a quick conversion of that to liters. And I'm going to whip out my calculator. And I am going to calculate how many moles of NaOH were dispensed into our H2SO4 solution in order to reach the equivalence point. So 0.950 times 0.0255 is going to give us 0.024225 mole of NaOH. Liters cancel. Now the question is, how many moles of H2SO4 would this amount of NaOH react with? Well, we have to use the mole-to-mole ratio. So we're going to put 1 mole H2SO4 on top. And we're going to put 2 mole of NaOH on the bottom. So we're basically dividing our NaOH by 2. And when we do that, we get, for our moles of H2SO4, we're going to get that that equals 0.0121 0.1125. Notice I'm retaining a lot of significant figures at this point, but we'll have to worry about how many we can actually keep at the end. Okay, now once again, we know that we had 20 ml of H2SO4. So I'm going to divide this by 0.02 liters in order to get my final answer. And I'm going to find out, wait a minute, 0.01211125 divided by 0.02. And I'm going to get a molarity of my sulfuric acid of, so this is molarity of H2SO4 at this point, which is our question, right? Molarity of H2SO4 is going to be 0.606 molarity, 3 sig figs. So M equals N over V was a very important tool to use here. And understanding that things like molarity times volume gives us number of moles. And in turn, this is N over L equals molarity. So we're basically playing around with this equation to get the answer that we need. That's all, folks.